Okay, section 3.4, approximation and relate rates. Okay, here, in this section, we're going to take a look at applications to get the tangent line. We consider linear and quadratic approximations, which will be extensively studied in the later chapter 9. Okay, first we start with the linear approximation. Suppose we have a differential function y is equal to f of x, y equal f of x like this. Then at the point a and f of a, we may think the tangent line at there. We can find this tangent line L of x with the derivatives of the function f at a in this way. Okay. From this graph, this is the equation L of x. From this graph, we can see that near x equal a, the tangent line and the function have nearly the same graph. 여기 요 점 근처에서는 요 곡선과 요 탄젠트 라인이 거의 비헤이비어가 같죠. 거의 다 같이 직선이죠. 그러니까 우리는 요 부분에 대해서 지금 공부하려고 하는 거예요. Okay. We will use the tangent line L of x as an approximation to the function f of x near x is equal to a. Okay. This tangent line is called the linear approximation to the function at x is equal to a. Okay. This linear approximation do a very good job of approximating values of f of x as long as we stay near x is equal to a. Okay. Let's take a look on one example. Determine the linear approximation for sin theta at theta is equal to 0. Okay. What are we supposed to do? First, find the first derivative of the given function and find the derivative at that point, at the given point, theta is equal to 0. Then with those informations, we can find the linear function, linear approximation L of x at x is equal to 0, like this. So L of theta is equal to theta. So linear approximation of this function near at theta is equal to 0 can be written as L of theta is equal to theta. What that means is if theta stays small, if theta is very small, then sin theta value is almost same as just theta. Okay? Okay. This linear approximation is one important example of the approximation. Then we will expand those concepts to the quadratic equation. Before that, we introduce a concept of differential. Okay. For a given function y is equal to f of x, dx and dy is called differentials. And the relationship between those dx and dy can be given in this way. dy is equal to f prime of x times dx, because dy over dx is equal to f prime of x. Okay? And this f prime of x dx will be called the differential of f of x and denoted by dy or df of x. Okay, then we can write this equation in this way as well. dy is equal to f from x dy. df is equal to f prime of x dy instead of dy. Okay. 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 We can have the we can find an application of the differentials in this approximation process here. Okay, since dy is the increment of the y coordinate to the tangent line, while delta y is the increment of y coordinate to the curve. Suppose we have a curve like this, then dx and dy is a different name of these differences on x and y axes for each functions. One for the given function, one for the tangent line at the point P. So the difference between delta y and dy is very small compared with the small quantity delta x. If delta x is very small, then the difference between dy and delta y should be very small too. Okay, so the limit of delta y minus dy over delta x when delta x approaches to 0, then this can be written in this way, which can be simplified in this way, and the limit of delta y over delta x when delta x approaches to 0, that can be written as f prime of x. So f prime of x minus f prime of x should be 0. What that means is when delta x is small, then the difference between delta y and dy is also very, very small. Okay. In other words, df can be used for approximation of the increment delta f of x. So instead of this value, we may use df. Okay. When x is keeps near at a. So we may write f of a plus delta x is almost same as f of a plus df of x. So with this concept, we can find the approximation of the given values. Okay. Okay. Here, these are the notation for these differentials. Okay, the df at x is equal to a can be written as f prime of a times delta x. So this value can be found by this equation. What that means is if we have a df, then just substitute x is equal to a, then we can have this much of difference with the differential. So see. The example 2. Use differential to approximate square root of 98. So, for finding the approximation of square root of 98, we set f of x is equal to square root of x, and that x is equal to 100, then delta x must be minus 2. Since df is equal to delta y, so df can be written in this way, and df at x is equal to 100 is minus 1 over 10. Then from the formula that we have developed here, f of a plus delta x is almost same as f of a plus df of y. So we can write square root of 98 as f of 100 minus 2, which is approximated by f of 100 plus df at x is equal to 100. Since this value is minus 1 over 10 and the f of 100 is 10, so 10 minus 1 over 10 is the 99 over 10, which is 9.9. That's the way to use differential for the approximation. Let y be a polynomial like this, then use the differential to approximate the value of y at x is equal to 1.997. Okay, let's see the solution. since 1.997 is equal to 2 minus 0.003, so we can think minus this value as a delta x. Then since we have dy over dx is equal to 4x cubed minus 6x squared plus 9 from this function, so the differential dy can be written in this way. Okay, then our approximation y plus delta y at the point x is equal to 1.997 can be written as y, which is 25, which y is the 25, and the dy value at x is equal to 2, which is minus 0.051, which fills out this position delta dy, so we can find the y plus dy as 24.949 with the differential. So same equations were used to find the approximation of it. So I tried to find the approximation, the exact value of the function with the SAGE tool to find this value. Compare these two values, then delta y minus dy is only this, which is very small. So we can conclude delta y is very close to dy from those examples. Okay, so okay, so that's so you can rely on those approaches to approximate the value of the function at a certain point. Okay. Sometimes the better description of the error can be given by the relative error, which is computed as the error dy divided by the total quantity y, which is this. So we call this the dy over y as a relative error. So. And percent error is the one that is obtained from here by multiplying 100%. Okay. With those notion, the next example shows the radius of the sphere was measured and found to be 5 centimeter with a possible error in measurement of at most 0.02 centimeter. Then what is the maximum error and relative error in using this value of radius in computing the volume of the sphere? Okay, here, since the equation for finding volume is this, as you know, when r is a radius of the sphere, and then we can find the dv, which is 4r squared dr from here. Then we wanna have so at with air. Okay. Now, we supposed to find dv and dv over v when r is 5 and delta r is 0.02. Since dv is equal to 4 pi r squared dr when r is equal to 5 and dr is very close to 0.02. So by substituting those two values in this formula, so we have 2 pi plus minus 2 pi c cube centimeter, and at 5 we have v. So the relative error is dv over v, which is plus minus 2 pi over the volume when r is equal to 5, which is plus minus 2 pi over 500 pi over 3, which is plus minus 0.012. So this shows if we have this much of the possible error, then the maximum error doesn't exceed plus minus 2 pi cubic centimeter, and also then the relative error can be controlled in this. If we want to make this relative error smaller, then we should have a better measurement on checking the radius of a sphere. So by developing the measurement here, we can always control this relative error as much as we like to have. Okay. Now, the quadratic approximation. Okay. In the above, we considered the linear approximation for a curve, but the cosine function, this is a graph of a cosine function. The graph of cosine function is very nice looking curve, as you see, the cosine curve. But the best linear approximation for the cosine function near 0 is quite unexciting. Because x equals 0, what is the tangent line at the of the cosine function when x is equal to 0? That is just a horizontal line. Okay? So, but like this, L of x is equal to 1. But the difference between these two functions are so big, so the linear approximation does not work well for certain curves. So we need to think a better approximation for the general curves. So we now consider the quadratic equation of over the linear approximation. So we approximate a curve by a parabola instead of a straight line. So we will look for a second degree polynomial like this. P of x is equal to a plus bx plus cx squared, like this. So this must we will show this approximation is better for the approximation of the given curve near x is equal to a in general. Okay. So in order to find the second degree approximation, we need to know those coefficients. In order to get that approximation, we will use the first derivatives and second derivative of the given function. Okay. So for the function y is equal to f of x, if then P of A can be found by f of A, and P prime of A can be found as f prime of A when y is equal to f of x, and P double prime of A is same as f double prime of A. So those can be replaced in this equation to get this. When f of x is sufficiently smooth, that means it's differentiable and second differentiable and continuous. Okay, we call this P of x is a quadratic approximation for y is equal to f of x near x is equal to a. So with this second degree approximation, let's find out a quadratic approximation of the cosine function. Okay, before we had the linear approximation for the cosine function. Now we're going to have a quadratic approximation for the cosine function at a is equal to 0. So P of x can be written as f of 0 plus f prime of 0 x plus f double prime of 0 over 2 x square. Here x square is missing, x square. Then since this f of 0 is equal to 1 for the cosine function, cosine 0 is 1, and f prime of x is sine x, so sine 0 is 0, so this term is 0. So we have 1 plus 0 plus f double prime of x is minus cosine x, which is, so the double prime of minus cosine 0 is minus 1, so we have 1 plus 0x minus 1 over 2 x square. That's what we have, like this. So this, so let's consider these two polynomials, two curves. This one is a cosine function, and this p of x, which is 1 minus x square over 2, is a curve like this. So these two curves are pretty much similar on near the x is equal to 0. This shows this quadratic approximation works very well near a given point, like this. Understand? Not like the linear approximation. Linear approximation was just a straight line, which is totally look different than the cosine function. Okay. We use this quadratic approximation to find the approximation of a given specified value. Okay, here, let's find the quadratic approximation of the given function y is equal to square root of x plus 1 near x is equal to 0. Then use it to find the approximation of square root of 0.99. Since the quadratic approximation of this function y is equal to square root of x plus 1 is this from the given equation, like given equation, the given quadratic approximation of y. So we have p of x like this when at x is near 0. Then square root of 0.99 can be written as 1 plus 1 half of delta x minus 1 over 8 of times the square of delta x, which is 0.01. Okay? So that's close to 0.9949. So we can say the approximation of square root of 0.99 can be written as this by the quadratic approximation. Yeah. When we checked it with the exact computation, the difference was matched up to the 6 decimal places, which means they are very close. Okay. So this quadratic approximation works very well for the curve, for the general curves over the linear approximation. The last part of the section 3.4 is related rates. This is one of the application of the differentiation. And okay. The reason that we are learning this relative rate is in the real world, many quantities are related with each other. So their derivatives will be related with each other as well. So this is after the useful approach to the solution of real-world problems. Let us consider some simple examples. Here, example 7 says, here's the balloon is released at a point 100 meters away from the observer. Here is the observer, and the balloon is here. this S is 100, who is on level ground. It's level ground. The 100 meter here. If the balloon goes straight up at the rate of 5 meters, so balloon starts from here, go up with the rate of 5 meters per second, then how fast is the distance from the observer to the balloon increasing when the balloon is meters high, 50 meters high? Okay, so when this height is reached at 50 meters, then how fast this distance changes? So what we need is the ds at a certain time, that when h reaches at 50 meters. So let's formulate the relationship between these three numbers with the Pythagorean theorem. So s square is equal to h square plus 100 square. So from here we can find ds dt by differentiating both sides with the time t. Then we found ds when h is equal to 50 and the rate of the balloon, the rate of change of that means dh over dt is 5. With these informations, we can deduce the s ds over dt. Since s is equal to 50 over square root of 5 at that time. So ds dt can be found with these three informations, which is square root of 5. So this square root of 5 is the speed of the balloon when the balloon the distance between the observer and balloons. When this balloon reached at the height of 50 meters with the speed 5 meters per second. So that's the way to find the changes, because this change depends on the change of this distance. So we can always find one other from the given informations. So we can rewrite the conclusion by this. At h is equal to 50 meters, the distance between the balloon and observer is increasing at a rate of square root of 5 meters per second. That's the way. The same thing can be done on the moving car on the highway. So speed camera can detect. So what the speed ticket can be issued with this kind of the mathematical simulation. We can also use this differential to approximate such a value, 30 degree and 30 second. This 30 degree and 30 seconds can be written in this way, which is written as this. So 30 degree is 30 over 30/60 times 2 pi, and 30 second can be written as 30 over 60 times 36 times 100 times 2 pi. So this can be written as 2 pi over 12 plus 2 pi over 120. Okay. So that is 6 over pi plus pi over 60. Okay. Pi over 6 plus pi over 60. So this value, so sine theta, sine 30 degree and 30 second can be written in this way. This can be approximated by linearly by f of x plus f prime of x plus delta x, which is pi over 60. So we can do the computation in this way. we find sine x. So we can find the left-hand side with the sine function with this. From the numerical approximation, we have 0.544. Okay, this is the exact value from the left-hand side. If we use the differential, then we find f of pi over 6 plus dy at x is equal to pi over 6 and dx is equal to pi over 16. Then the numerical approximation of that value can be written in this way. As you see, those two values are almost the same. We can do the things in here. So let's see. So we can find the approximation here. Let's see. So first, find the numerical approximation of that value, which is 0.507, etc. Then the numerical approximation of the other value is what? Can be found in this way. Let's compare those two values. Let's see. The difference of these are almost the same up to what? Decimal point 5 or 6. So those two numbers are almost the same. So for the approximation, you can usually use the differentials instead of this. But now, with this computational tool, you can use either ways. So before, without this computational tool, you couldn't find this by hand, but you could do this with the knowledge of calculus. But now, with the computational tools in your hand, that doesn't make a big difference. Okay? So that's why you are living in the different world. So you should be able to utilize all the possible resources to deal with your own problems. Okay, here's the examples. There's lots of examples. Find the approximation. You can do the differentials like this. Find the dy and find the linear approximation to get the approximation. Okay. See, this is the approximation by the linear approximation. This is the exact value by the computer. As you see, there is not much of difference. 2.006 are almost to are same. Same things are done. You may use the SAGE tools to deal with such problems as well. Okay? I think that wraps up the chapter 3. Any questions?